AOG Gaming here. Hello, everybody. AOG Gaming here. Back with another video. So give me a sec. Um, yeah, I did some thinking on what the crystals can do, since they are both magnetic and heliomagnetic. Um, or at least that's what the paper said. Like you can basically change the form of the papers by applying pressure, which you can do with magnets, is how they did in the experiments. um, to basically change the shape of the crystal. So I was thinking, okay, what is a really good way we can apply that? Well, holographic projection. So what you do is you're using the Faraday effect. If you don't know, ferrofluid between like two sheets of glass, and then you put light, you filter light through it or something, and you use magnets. You can actually control where the light ends up. Um, but I was thinking of taking it a step further, and if, instead of just using regular magnets, to use superconductors or quantum locked magnets, whatever you want to call them. So basically, what this would do is this would send the photons, like you could bend the photons in a specific way. Um, I'll get to how it's built first, but this is like my thinking process of like how I would explain it. So because the photons are able to be bent with magnets when they're passed through the ferrofluid, we use the crystals to filter that light itself after it comes out. Um, Here's the thing though, this crystal is both ferromagnetic and it can also have heliomagnetism, which is a specific type of magnetic field. Now, why this is very important is because one, if you just wanted the crystal to reflect the light, you could have it bent a specific way where it just reflects at an angle, and then the angle of change basically determines the path at the moment of observation as it hits the crystal, which is the light itself. Um, oh, okay, that went away. Wait, give me a sec. So my camera keeps closing. So yeah, you could change the angle and then basically determine the path of the photon simply depending on the crystal itself. Now, how you change the shape of that crystal very easily in a giant array is you do what I call a ferromagnetic crystal or magnetic crystal array. Basically, you have a grid made out of magnetic material that when you apply charge through it, it basically pushes in on the walls of the um, grid. And what happens is it's not a super tall grid. It's going to be super thin, obviously, almost, maybe atoms thin, whatever. And basically, what will happen is you'll be able to control the crystal. So the crystal would be like the ball right here. It controls the crystal by putting different amounts of pressure on each side. So you put more on the left, more on the right. Basically, what happens is you're able to control how the crystal moves in time, and you're able to basically change the angle. So you're going to be changing the angle like this, kind of like that, of the path of the light just by bending the crystal using magnetism. Now, you can't shoot light sideways. That was just a crude example of what I did. But a better way would be to actually shoot light through the other way. So before we move on to that, though, I just want to explain this real quick. This is the most basic way of doing like the grid, right? It would shoot its quantum locked or its superconducting field straight up, and it would pinch the magnets. I call it the magnetic pinch, in between a layer. Basically, you could also put another magnet on the side to basically more magnets on the side to keep it contained. But then again, you would lose the like being able to actually use the hologram because it'd be covered on all sides, obviously. Because this side definitely has magnets. That's the whole point why the magnetic pinch works. But it's just to like determine the differences between how simple it is to do it, whether how complicated it is, but it's also a different way they use it. So let's move on to the next page. Here we go. This I drew a lot less of because I just wanted to explain it more. So here was my thinking, right? Using a superconducting magnet is not super efficient, right? One, you need to have the photon in front of the magnet or above it or whatever. It basically has to be in front of whatever the face of the magnet is quantum locked and shooting the magnetic field in its opposing direction, based what the way that it's facing. Um, so what will happen is you will have to have like a light here, a light source somewhere getting here, and then actually being able to, push the magnet itself. Otherwise, you get into the complications having a photon going through a crystal like that, and then you have a magnet here, and then you have to like, align. But with quantum magnets, it might be easier because, again, it does spin freely. That's the problem. So it might spin in like around it this way. which is not very ideal, especially if you're trying to control the magnets. So instead of using that, I said a crystal is better. What the crystal will do is it'll be able to both deform, and you're just able to shoot a straight beam of light through it, which will, allow you to control the magnet however you want. And because it's ferromagnetic or magnetic, you can basically induce different types of magnetism on it using the magnetic grid I was talking about before, basically crunching the lattices of the actual crystal in different ways using that magnetic pressure. This may take a lot of power, so it's probably not possible right now, but once fusion is through, this could possibly be like a very cool and very easy thing to do. Um, then basically what will happen is you can either do heliomagnetism or straight magnetism. I think the heliomagnetism might actually be the thing that makes or breaks the basically how to control the light waves. Because if you know how a photon travels through space, it's kind of like a corkscrew rather than um, you know it's not really a corkscrew. It's kind of is. So like basically it would look like this because electric and magnetic properties. Basically, that's what I'm saying. So it kind of looks like this. It's like that. That's the way to draw it. I don't know else how to explain that, but that's how it travels through space. But you would have to actually determine its position in moment and in time. So you might have to use square waves actually, which would be like that. Um, so you would just use the square waves to determine that position, or you can use the heliomagnetism to actually, change you would also have to use the square waves, but it would be in the like basically the shape of the corkscrew that is produced. The corkscrew is the magnetic field. That's what I'm talking about. So the corkscrew would basically go. The magnetic field would turn like that. That's what the heliomagnetism is. And then what it's like a helix basically. And then what that would do is it would allow you to basically, change the magnet in whatever direction to control the light wave in a certain way. And then you could be able to hit the particles very directly and very precisely to basically bunch them up into like a center and be able to create an image, like, but in 3D space. So you would have to. This is what my crude drawing of what the machine would look like. So you have the table and you have a lights, also another light source from above, or you could just have magnets on the top, but it gets complicated on deviation. So I just like copied exactly what was on the table in the bottom. And the easiest way to do that would basically just doing pyramids. So you bend the magnetic fields in a way where it either goes straight to the center like that. And ways you can do that is basically doing this, or you can have what I was showing here where they actually curve inwards instead of curve um sorry, they curve exponentially here and they curve logarithmically here. That's just like the difference between how the magnetic fields would actually look like as they're manipulating the light source coming through. Now the actual tables in themselves would have to have the ferrofluid like at the bottom basically, but like as soon as that's basically the last layer the light hits before it exits the machine, but the magnetic field is still being applied, right? Because it can go through the ferrofluid. um so that's going to be really cool. It'll basically allow you to manipulate the path of the photon both in time and in difference. And the best way to basically make this so that you can do like brightness, you can do um obviously different colors. You have a basically a laser array that shoots through the crystal that is heliomagnetic, and you can change its shape, depending on obviously the magnetic grid. Though it's going to be really hard to actually no. So for heliomagnetism, I don't think you would have to change the actual lattice structure of the magnet or the crystal, because it's a magnetic crystal of the crystal, because of the way that the atom travels itself, which is because of the heliomagnetic path. It's able to basically push it on. It's basically able to counteract how the photon travels through space and time, and you're able to actually control the photon. That's what I'm trying to get at. um, so you would have multiple lasers array. Obviously they would shoot through the same opening, and that's dependent on how many photons can be spaced in between. And you would also have to like account like the distance, whatever the square or the basically the distance between the atoms. So basically you would have something like that, and then the light would shoot straight up from here basically like at you. That's what you're imagining. This is like the top view. um, so you would have to like account for where the lasers are placed basically, and that's going to take probably a quantum computer. So that might be a little bit harder. But if you do single atoms and you just make a single lasers for single photons, or packets of photons at a time, but in length like this, which is where I'll talk about that in a second. You can basically make a giant massive array, and it would have to be really small lasers, but it would work. It would just be have to be really small lasers. And then the brightness, you could choose a wavelength that's really close in like wavelength. I was thinking basically to the light, but then I realized that's only possible if you have multiple lasers shooting through one crystal at a time, which is going to be a lot harder than just having one laser. So for one laser, you would basically change the distance between the packets of photons that are traveling. So you would turn on and off the laser basically, and the closer those times are apart of you turning on and off the laser would determine the brightness, because of the packets of photon that are being packed in at a moment's time. And obviously, the frames per second, the wavelengths would have to be high enough so that we can't physically see the differences between the distances, obviously, which would be much harder to actually stop the light, rather than just let it would be more wasteful actually than just letting the light shine through. So very cool. That was like my big breakthrough right there. I was thinking, oh, this is like a totally different, and it's the Faraday effect, I believe that's what it's called. Don't quote me on that, but I think that's when you know bend the lights with magnets using ferrofluid shining through. So that's just what I'm going through. And then obviously it would have to be very precisely controlled ferrofluid. You would have to still have superconductors or quantum magnets if you want to do this. I think for the most part, you could use regular magnets, but then you get into a much more complicated scenario, because actually the light bends to the magnetic field, which is why I say having straight magnetic field is much easier, because all you got to do is now bend it a certain way, like you're just bending the magnetic field a certain way. That's it. But yeah, I don't know. So that's cool. You could also just like spin the crystal itself and just have the light source shine through it, but then again you would have to have the lasers on a swivel with the crystal shining through the actual table of the film. And yeah, there's a lot of complexities that come with it. But this is like probably the closest I think you can get to manipulating light using the Faraday effect to basically create a hologram. But you would have to also use superconductors. I think that's the problem, right? Because the heliomagnetism, I think it goes like that, right? Like it curves like this, kind of, like it curves around it, but it's not a very it's more like it spins basically. It's more for spin. But I think it will work the way I'm thinking of. It's just it'll be very hard to use it in a very specific way. So there's a lot of complexities, but it does seem very promising. So just wanted to share that with y'all. As always, thank y'all for watching. AOG Gaming here. Um, yeah, that's pretty much it. And this is probably the last video for like a while, because I have to do other content, and I'm just rambling at this point. Anyway, thank y'all for watching. 158 subscribers last time check. We're increasing a lot. I'm like excited, but I also got like 8 days before I'm just like not able to feed myself. So I don't know. We'll see how long this lasts. If I'm able to renew my swipes, then I'll tell y'all. But if I'm not, then don't be surprised if I just, oof, you know. Um, yeah, that's it. As always, thank y'all for watching, and I'll see y'all in the next video.